our topic, our first official topic in the course, the history of computing. Now, I admit some people might think that this is dry and boring and not very practical, but I'd like to think that in order to appreciate the technology that you have in front of you, or with you, or that you use on a daily basis, it helps to know what technology we had 10 years ago, decades ago, hundreds of years ago, and what progress we've made since then. So one of the interesting facts is that the computing power of the guidance system used to put astronauts on the moon, the processing power there is actually less than the processing power of, let's say, some high-tech appliances now. So just to show you the kind of advancements that we've achieved. So we start with the abacus, and you've probably seen something similar to this, if not an abacus like this. And this dates back to thousands of years BC, where ancient civilizations use it to count and to add values. So essentially what you have is a series of beads or knots that are tied onto to string, and the number of beads, the number of knots, and their positions determine what the value is. Now we'll be getting into more details as to how that value was represented. In fact, we'll be looking at the abacus again later on in the course. I bet you didn't think that would happen. But we will be taking a look at the abacus again later on in the course, and we'll be talking more about it then. Sometimes if you're playing an informal game, sports game, or pool or darts or anything like that, and you're keeping score, sometimes you're moving beads along a string or a wire just to keep score. Essentially, it's the same thing. You have been to a kindergarten class. You might have seen a toy like this. Essentially, it's an abacus, where the child learns to count by moving beads along the string or the wooden bar. We move ahead to the mechanical calculator. So what this does is essentially does the same thing. We have different digits here. Each wheel is connected to a little display which displays a number. And you can increment or decrement, you can add to or you can subtract from that value by turning these wheels either clockwise or counterclockwise. The interesting thing about this is, as you turn a wheel, suppose you start off with the value of 1, and you keep turning the wheel, so it increments to 2, 3, 4, 5, 6, 7, 8, 9. If you increment it again, the wheel next to it, to its left, will rotate again, will rotate and essentially carry that value. So past 9, when you add 1 to it, what do? You carry the 1. Well, this dial will then reset back to 0, and the gears will cause the next dial to turn one place. So essentially, it performs the carrying for you, simply by turning these knobs, and you can increment by a certain amount. And of course, if you wanted to subtract, you would simply turn the opposite way. So this design and this device here was invented and designed and implemented by Blaise Pascal in 1642. But, at the time, it was believed to be the first design of the first mechanical calculator. But in fact, centuries later, it was discovered that a different person, Wilhelm Jacquard, in 1623, actually designed and had written down designs for a mechanical calculator, independent of Blaise Pascal. Unfortunately, he never got a chance to implement it, and the design wasn't worked on. He died, and his notes were lost, again, for centuries. And then it was revealed that these designs predated what was believed to be the first mechanical calculator, and so now they share credit posthumously for the invention of the first mechanical calculator. Does anyone here knit or sew or do anything with textiles or fabrics? Same response I got from the other lecture. Okay, so in creating a design in fabric, that can be very time-consuming, very challenging, very difficult. back in the early 1800s, there were looms, and looms are used to create fabrics and textiles and put patterns in them. But what Jacquard did, this inventor called Jacquard, he created a loom that took punch cards. Punch cards are essentially pieces of paper, cardboard. You might have recognized it a few, well, perhaps not. Several years ago in the States, they sometimes still use punch cards for voting in the presidential election. Anyways, punch cards were used in computers and in machines dating back centuries. People would punch holes in the cards in a certain pattern. Jacquard's loom would read in this pattern of punched out holes and translate that into a pattern to be sewn in or woven into the fabric. And so with a specific punch card, a series of punch cards, this loom back in 1801 was able to produce fabrics such as this. And so the ability, I mean, people were able to do this by hand. Make no mistake about that, they were able to do that by hand, but it was very time-consuming and laborious. And so it garnered a very high price tag because, of course, if something takes a lot of effort to create, typically it's valued more and costs more. But this was able to automate the process. Jacquard's loom was able to automate the process, bless you. And as a result, the cost of producing these textiles was decreased. And this is an example of the first programmable machine, because you could take this loom, feed it one set of cards, and have it produce a specific pattern. You could then feed it a separate set of cards and have it produce a separate set of a different pattern, perhaps on the same fabric, perhaps a different fabric, and you could customize it according to whatever product you wanted to create and sell. Next, we come to the analytical engine. And I just wanted to keep an eye on the time, and we have a little bit more time. And so this is considered the first general purpose computer. This was invented by Charles Babbage back in 1834. Unfortunately, it was never fully developed. So components of it were developed. Basically what it is it's a large mechanical structure where you would turn a crank, or someone would turn a crank, and based on the positioning of the gears, it would calculate certain values. Initially, it would be used to calculate terms in polynomial functions. It was later designed or programmed to calculate Bernoulli numbers, which is a mathematical sequence to represent trigonometric functions. So it was never fully realized because to implement this cost money. And so he lobbied for the funds from the British government, and they provided some funds for him, but then it came down to logistics. He spoke to some engineers, and what he needed to be designed, the engineer said at that time was not possible. So in fact, what was available at that time, the technology available at that time, did not allow for this to be implemented. There was another invention by Babbage called the difference engine, and again with that, the designs for the difference engine, similar device, similar mechanical features, were outlined in designs and drawings and illustrations, and it only came to light relatively recently. Someone decided to launch a fundraising campaign, almost like Kickstarter, to raise some money to actually implement the device. The device is very large. I think it was completed in 2013 at a cost of approximately $200,000 of today's money. So $200,000 of today's money, imagine with inflation what that would have cost back in the 1800s. So it's not surprising that it wasn't fully realized in the day. As I mentioned, this is considered the first general purpose computer because even though it can compute certain values, you can change the gears, you can set the gears in such a way that the values it computes, or the function it computes, can be changed and can be set. And so someone that he was working with at the time, who was interested in his work, Ada Lovelace, designed a computer program or specific set of instructions for the engine to generate Bernoulli numbers. And it had various characteristics of a program that we recognize even in today's programming programs and programming languages. And so she's considered the first programmer. And so a lot of people are surprised to learn that, because typically now when you think of a computer programmer, there's a difference in the number of men and women in the field. Computer programmers are mainly men. And so one of the aspects of this presentation is to highlight the contributions of women in computing history, to increase the recognition of women in computing, and also to gain, to hopefully encourage interest in technology. Lassonde has launched a 50-50 initiative in hopes of raising the number of women in studying engineering and technology to be that, or close to that, of men, hopefully by 2020. So we're certainly hoping for that. So Ada Lovelace is considered the first programmer, and it's for her work with the analytical engine. That was the first general purpose computer, but the first electronic computer is considered to be ENIAC. Remember, the analytical engine only works if you manually crank it, if you manually turn the crank and get it to perform the calculations. But ENIAC was an electronic device. To control the flow of electrical signals, it used vacuum tubes. Vacuum tubes are similar to incandescent bulbs in many respects. It's called a vacuum tube because the air inside is sucked out of it to improve conductivity, and so there's nothing left inside the tube, so it's considered a vacuum, lack of anything there. There's some problems with vacuum tubes. They're large. I mean, they're physically about the size of a incandescent bulb. They generate a lot of heat, again, like an incandescent bulb, and they're prone to fail, again, like an incandescent bulb. So for practical reasons, it wasn't really feasible to continue using them. Thankfully, technology has advanced, and identical electrical characteristics are now provided by transistors. Transistors that can be so small that they're microscopic. In fact, the processors in your computers and smartphones in front of you probably have billions and billions of transistors in the area of less than a square inch. And so we've gone from probably a few thousand vacuum tubes in a single computer occupying an entire room. Here you can see ENIAC, and you can see it's quite massive, to billions of transistors on a chip that you can carry in your pocket, or even a wristwatch. So how exactly was this computer programmed? In order to program it, in order to get it to compute some values, you had to enter in values. You had to enter in instructions, and one did that by setting various switches. And so designers would come up with the algorithm, the set of instructions, and programmers would actually stand there and set all the switches accordingly to that program. For ENIAC, it was a total of 6 programmers working in a team, all of them women. So again, women programmers were the norm in the early days of modern computing. And here's a list of all of them. In fact, here's a picture. I believe the caption stated that this woman here is Betty Holberton. So the woman in the middle here is the woman pictured in the image. So again, these programmers would go through and set the switches all manually. I mentioned before about the amount of computing required to send astronauts to the moon. In the late 60s, it was the Apollo space program, again devoted to sending astronauts to the moon and back. The amount of computing required was quite considerable. So IBM mainframes, IBM, a major company, they manufactured large computers, mainframe computers back then. They still do now. And a lot of the trajectories were calculated using those mainframe computers. But in addition, there also had to be a computer on board the spacecraft, in order to calculate the specific navigation. There was an analogy as to the amount of precision that was required. If you were to build a scale model of the Earth and Moon and the trajectories, the Earth would be the size of a basketball, and the moon would be the size of a baseball, placed 14 feet away. And then the amount, basically the target area that the spaceship had to navigate towards was the width of a sheet of paper. And so with that amount of precision, computers needed to be used to essentially autopilot or fly-by-wire the spacecraft and have it meet its mark. Interestingly enough, as I mentioned, the processing power of the early computers in the Apollo program had less processing power than a lot of the modern day appliances. Again, there was a team of developers who developed the programs and the algorithms, and there was a separate set there was a separate team led by Margaret Hamilton who actually coded and implemented that program. And so here we have a picture of Margaret Hamilton, and if you're wondering what she's standing next to, that is a printout of the software code used in the guidance computer. And so that's how much code was required in order to perform the capabilities that were required. She's considered to be a pioneer in software engineering. The story is that she would often be testing the programs in the simulator, and she realized one day she accidentally loaded a program into memory while another program was running, and that caused the computer to crash. And so she brought that to her superiors and said, we should put in some safeguards for that. And they said, nope, no worries. Astronauts are trained to never make mistakes. Okay? Well, it turns out in Apollo 11, I believe, an astronaut accidentally loaded a program while another program was running and crashed the system. And a lot of the information had to be re-entered into the computer manually. But thanks to some of the safeguards and the error control, the error checking that Margaret Hamilton had implemented, the disaster was averted. So that's one of the aspects of software engineering, and she was considered a pioneer in software engineering. I mentioned IBM before, and this will be the last slide that we cover for today. So I mentioned IBM before, and a lot of people just know IBM as IBM, but IBM stands for International Business Machines, and they started creating machines to conduct business, accounting, and all that in the early 1800s. In the 1890s, they started creating computerized machines. And in the 1960s, they were very popular for creating mainframe computers. These are large-scale computers that they would sell to businesses, especially accounting firms, to calculate large numbers of values, large quantities of financial information. They would also sell it to the government. The government would be using it for census information, census data. So calculating the average age, processing the average age, mean age, stuff like that, number of women, number of men, number of people within a certain demographic. All that would be calculated, vast amounts of data. All of that would be calculated on servers, mainframe computers. And now IBM still works with servers. Deep Blue and Watson, they were used for artificial intelligence and they were demonstrated in chess competitions and online on television on Jeopardy, but they're also used to simulate other situations that we can't directly manipulate or examine. Subatomic interactions, drug interactions, weather phenomenon, things like that. But in the 1960s, IBM was played a key role in developing ways of processing information to speed up the performance of computers. And essentially, up until that point, computers would perform a task, and then perform the next task, and perform the next task. Sometimes, when performing a task, the computer would have to wait for additional information to become available or to be fed additional input. IBM and the team called on the Advanced Computing Systems Project came up with a novel idea at the time, but now it almost seems intuitive. And it's basically time management. Suppose you have a project due, it's a group project, and you have to wait for a team member to complete their part of their project. Well, you could sit around and wait, Or you could use that free time to work on a separate project that you might have for another course. So what IBM came up with, and the team at IBM Research came up with the ability to execute instructions out of order, out of the original order. And they were able to do that within the computer because the computer was able to look ahead and determine what instructions depended on what information and what other data. So one of the key players in creating that was Lynn Conway. She was on the team in 1964 to develop this sort of architecture. Now, not much is known about Lynn Conway in the early years, and that's because she was born a man. And so she realized she identified as a woman, and so in 1968 she transitioned because it was very uncommon at the time. She feared the backlash towards her family, so she created a new identity, and she changed her name, created a new identity, and because she had made so many important contributions to IBM, she was expecting to go back there. I learned about this when I went to the Computer History Museum in San Jose, and just outside San Jose, and the tour guide there was mentioning, and because she was coming back as a woman, IBM cut her pay. And so that was supposed to be a joke. The sad reality is they didn't cut her pay, they fired her because they didn't want a woman working as an engineer. So thankfully she had some friends still on the team who went through some of the records and changed the name on the records to her new name so that she would still get credit for all the accomplishments she made as a man with IBM. And so thankfully, she's still given credit for a lot of that. After being fired from IBM, she joined Xerox PARC. How many of you are familiar with the name Xerox? Some of you probably have heard about that and probably associate that with photocopiers. Well, Xerox actually had a research group called Xerox PARC, and they are responsible for a lot of innovations in technology that we sort of take for granted now. We'll be covering that in the next slide. But she went on to work with Xerox PARC and wrote the defining textbook on chip design. So it's quite impressive. Okay, so I will end the lecture there. I will see you next week on Tuesday. Have a good weekend. So we left off here talking about the International Business Machines Corporations, or IBM as it's more commonly known, especially now. Back in the 1960s, they were at the forefront of leading technology with regards to large processing power, large mainframe computers, and processing information in ways that is more efficient and could boost performance of their computers. We also highlighted the contributions of one individual, Lynn Conway, who was fired from IBM and then later joined Xerox PARC. So we mentioned how some of you might recognize the name Xerox from photocopiers. Well, in fact, Xerox had this Palo Alto Research Center. That's what the acronym PARC stands for. And that's where a lot of research was conducted, and a lot of technologies that we take for granted now, that always seems to come up at the same time. Thank you. That would be convenient later on when we talk about other aspects of the course, but thankfully it's out of the way now. The Palo Alto Research Center is a place where Xerox had a lot of research innovations, and they created topics that are taken for granted today. Yes? It is, yes. So close to Silicon Valley. So that's sort of, yeah, basically where everything happens, where Google is, where Xerox is, where Apple is a little bit over in Cupertino, Facebook, a lot of other companies. It's really interesting to go there and just even just taking the public transit system in certain areas, you look everywhere and you see these huge buildings devoted to IBM, Oracle, all these big names in computing. And interestingly, those are all on the public transit route to the Computer History Museum. So on your way to learning about computer history, you pass all these buildings that had very significant contributions to computer history. PARC was innovative in creating certain technologies. Ethernet technology is one of them. That's basically the network communication port that you use for wired communications. You might not have it on your laptops, but you certainly have it on all your desktops. You can see it in lecture halls. There's a network port over here. And that network port, that was created and that was patented by Xerox PARC. In addition to laser copiers, laser printing was also an innovation that came out of Xerox PARC, as well as object-oriented programming. Now, we're not going to get into programming in this course, but it is important to note the contributions of Xerox PARC in modern-day computing. Object-oriented programming is a way in which programmers write code that basically abstracts real-world concepts and creates objects that they can then manipulate. So if you were to create a program that was used to hold student information, you would have an object that represented a student with that student's attributes such as the name, contact information, student number, courses he or she is taking, so all that. And then the programmer would be able to manipulate that object to add courses to it or calculate a GPA, something like that. That concept is very prevalent in today's, in modern day computing, and that was created, that was one of the innovations that came out of PARC. Also, a lot of people think that the modern user interface in computers, a graphical user interface, or the GUI that's used in a lot of computers, came from either Microsoft or Apple. In fact, it came from Xerox PARC. They had two workstations that they developed for in-house use, so it wasn't commercialized, so it was just for their own use. One was called the Alto and one was called the Star. They both had an operating system that made use of windows, of icons, of menus, and used a mouse to navigate the user interface. And one of the members of the research team that contributed to the development of the GUI and also to an object-oriented language called Smalltalk is Adele Goldberg. She was famous for her contributions at Xerox, but not so famous that she could only use her first name. So here we have Adele Goldberg with contributions in object-oriented programming and development of the graphical user interface. So the story goes, her managers, her supervisors, wanted her to give a demonstration of this graphical user interface, the GUI, to a new up-and-comer in Silicon Valley by the name of Steve Jobs. And he had just created this company, maybe you've heard of it, it's Apple. And so he wanted to be given a demonstration of this new graphical user interface. And she was against it. She said, no, I don't think that's a good idea because he's just going to take these ideas and then we're going to lose market share. We're not going to be able to hold on to our intellectual property. The managers said, no, just do as we say, give him this demonstration. So she did reluctantly. She said, okay, but any ramifications from this, that's on you, not me. Well, after that meeting, Steve Jobs then developed the Macintosh operating system, which used a very similar graphical user interface, commercialized it, and the rest is history. That led to the Macintosh computers that were developed and sold very well in the 80s and went on to make Apple a household name. Later on, many years, Xerox tried to sue Apple because of the patent or copyright infringement, but the judge did not rule in favor of Xerox. He found that there wasn't enough proof that Apple had taken and stolen technology from Xerox. So perhaps they didn't take the actual code, but the concept of the graphical user interface was certainly highly influenced by the work at Xerox PARC that went on to lead to the innovation and commercialization of the Macintosh operating system, and that, some may say, was the inspiration for Microsoft to come out with their own operating system, a graphical user interface called Windows. And from there, we also have graphical user interfaces from our smartphones, our tablets, and our other many other devices. And so the contributions of Xerox and their Palo Alto Research Center is very significant. Next, we're going to talk about ARPANET. So ARPANET started as a very large area computer network, joining the computer science departments of 4 major US universities. And this was established in the late 60s, in 1969, and it continually developed. So it was established and communication was feasible back in 1969, but it continued to evolve and develop. And so additional techniques, additional protocols for communication were developed and released. And it is the communication protocols that were in place all around in the 1980s on ARPANET that served as the protocols that are used on the internet today. So in many respects, ARPANET was basically the internet was born from ARPANET, and the technology and the techniques and the protocols implemented for ARPANET went on to serve the internet. One of the most important aspects of any network, especially the internet, are pieces of our network devices called routers. These are essentially traffic cops who will direct messages, direct data over the network, whether it is a local area network within your residence or at home or the entire university, or if we're talking about larger area networks such as the internet. Routers play a very key important role. The first routers to use this internet protocol, or what would be used on the internet, was co-written by Ginny Straszczar, and so she actually made a very important contribution in computing and wrote the software on these, wrote the program on these network devices that would again serve to redirect and manage data on the internet. We now come to mobile computing. Now, this day and age, mobile computing is ubiquitous. Everyone has a mobile device of one form or another, cell phone, smartphone, laptop, tablet, something of the like. Back in the 90s, smartphones weren't available. The equivalent were something called personal digital assistants. Now, they didn't necessarily have, the first ones didn't have network capabilities, because at the time there was no internet, there was certainly no Wi-Fi that was widely available. And so people used it mainly to keep track of their contacts, just like a secretary would or a personal assistant would keep track of contacts and information such as that. That's what people stored on these PDAs. Now PDAs, they didn't have a lot of processing power, but some actually allowed you to work on Office documents, word processing, spreadsheet applications such as that, the like. And so you were able to do a little bit of computing on these devices. Now as time went on, you were able to do more and more on these devices. These devices did have a touch screen, but the detail and the quality of the precision of tracking where the touch occurred not specifically allow for actually typing on the screen. So you couldn't type on the screen like you do now. You were able to use a stylus and type out on an on-screen keyboard and enter text that way. But if you look at the bottom here, bottom of the screen, you'll see an area that's sort of left blank. And in that area, users were able to draw certain gestures that were then interpreted as text. And so with the Palm, we didn't have phone calls coming in because there was no cellular network widely available at that time, but people using Palm Pilot were able to enter text. They were able to enter text using a gesture alphabet called graffiti. And so here we have a description. Let's take a look at this. There we go. So I know I had this somewhere. So here we have a picture at the top of something called graffiti. And so this was the gesture alphabet. This was the way that you had to write your handwriting in order for it to be recognized by the Palm Pilot. Palm wasn't the only company that was making PDAs. Apple also made PDAs. Apple came out with a Newton, one called a Newton. And the perspective of Apple was, we don't want to force users to change their handwriting, which is a noble goal. Apple hoped to allow people to write using their own natural handwriting, and they hoped to recreate it accurately as transcribed text. But unfortunately, that didn't happen. And so sometimes, actually in popular media, one of the students in the previous lecture mentioned Newton, mentioned an incident where, or a video where they're talking about the Newton and taking a note on one's Newton, but unfortunately the transcribed text does not match what was intended.
Take a memo on your Newton. Beat up Martin.
And it transcribes to eat up Martha. So again, there were a lot of jokes poked at the Newton's expense, and so it didn't sell very well. The Palm Pilot was certainly a more profitable venture, and that's because the input recognition was a lot more robust. Why? Well, it forced the user to conform to its own alphabet. And so regardless of, let's take a look at this example here. Regardless of whether you wanted an uppercase A or a lowercase a, you would have to write in a certain way. You would have to put your stylus down, draw a diagonal stroke up and then down. And then once you lifted your stylus off of the screen, that would be transcribed as an A. An uppercase A or a lowercase a would depend on where you wrote it on that touch screen. So for example, in this case, uppercase letters would be written over on a certain region, and then lowercase letters would be elsewhere, and numbers would be separate altogether. So this is the only gesture that it would recognize as an A. That would not be an A, that would not be an A, that would not be an A, even if you wanted a lowercase a, that would not be an A. None of that would be recognized as an A. Only this gesture in the graffiti alphabet would be recognized as an A. And if you want, there are actually some people who are very fond of the graffiti alphabet, and so they've implemented ways to enter graffiti on modern smartphones. So you can probably get it for your Android smartphone. So one of the founding CEO, or the founding CEO of Palm Computing was Donna Dubinsky, and she led the charge of Palm Computing to release the Palm Pilot. She actually helped with the design of the development of the Palm Pilot and the graffiti alphabet and the popularization of the graffiti alphabet. So it's interesting to note how far we've come with mobile computing, where we've gone from this device that is probably a little bit larger than modern day smartphones that really just held contact information, serves one purpose that your smartphone does. And now we have smartphones that not only manage our contacts, but perform so many other features as well. So we've talked a lot about the contributions of people in computing history. We're going to talk about three additional ones. Grace Hopper was a retired US Navy Rear Admiral who made a significant contribution in computing. We've talked about programming languages and how typically when you create a program, you have to write computer code. Now, computer code, if you were to take a look at it, probably wouldn't be easily understandable, but you would recognize some English words that would determine what the program does. So you might have the word for that would repeat a certain operation multiple times for a specific number of times. or decisions that were to be made. If this were to happen, if this is the case, then do that. If some other situation is true, do something else. The benefit of having these programming languages is that it makes it easier to program and to generate code and create programs for computers. Another benefit is that you can write your code and then pass it to something called a compiler that will then translate it into machine language. And you would have multiple compilers for each individual platform, each individual system that you wanted to distribute your program on. That concept was created by Grace Hopper. She created the first compiler and one of the first programming languages, COBOL. And so what would happen is programmers would write programs in this programming language called COBOL. They would pass it to a compiler. The compiler would be written for a specific computer system. Back then, each individual computer that was developed by companies was typically different from other computers that were released. There was no compatibility because everyone was competing against each other. And so anytime you wanted to transfer your program from one type of computer to another type of computer, you would have to rewrite the program. Compilers improved the situation by saying, okay, if you write in this program code, and this programming code, then what you have to do is you just have to find the compiler for your target system and then compile your program to machine language using the compiler. So the compiler would act as a translator, translating this code to the particular system. And so she helped develop that. She invented the first compiler, and she helped develop the COBOL programming language. The COBOL programming language is not very popular anymore, but it was very popular, especially in the business and financial industry back in the 70s, 80s. And it actually led to, well, back then, to save space, a lot of programmers would store the year as 2 digits. So that led to what was called the Y2K bug, or the year 2000 bug. And why was that a problem? Well, the programmers saved space by only recording the last 2 digits of the year. But when the year 2000 came about, again, it would only save the last 2 digits, so you would go from 99 to 00. And the difference between those years would be 99 instead of the 1 year that was assumed. And so to fix all these old systems that were written in, whose programs were written in COBOL, a lot of old COBOL programmers were called out of retirement to help with this, this so-called bug, and they were asked to fix the program. An interesting story also related to Grace Hopper, the concept of a bug, a computer bug. That's a term used to describe something that is not functioning as intended. That was actually coined and attributed to Grace Hopper. She was working on some of the computers in the US Navy very early on. This was back when they were still using vacuum tubes and had these huge monstrosities of machines that were called computers. And something wasn't right. A computation wasn't coming out correctly. And her and her team investigated, and they found that there was actually a moth stuck in the system. So they pulled it out. They actually preserved it and included it in their notes. And it was simply associated with the term bug. And so that's where the term bug originates from, and it's attributed to Grace Hopper. In addition to Grace Hopper was born in 1906. Unfortunately, she passed away in the early 90s. Someone who was born after her, but sadly died before her, was Alan Turing. He made significant contributions to the field of artificial intelligence. So in AI, there is the concept of a Turing test. And some of you might have heard this referred to in popular media, in movies and that. A Turing test is basically, in a general sense, is a test to determine if an artificially intelligent machine could actually pass as a human being. So the test in a general sense is, if you can converse with an artificial intelligence, an AI, and not realize that you are conversing with an AI, that means that the system has passed the Turing test in a very general sense. He also created the concept of, there's also the concept of a Turing machine, or an aspect in computer theory to test to see if certain problems that we have are computable by machines, computable by a computer. Not in necessarily a practical sense, but just is it something that a computer can compute and produce an answer to. There's also the contributions he made to cryptography. That's basically encoding some message or encrypting some message so that the original intent is hidden, or the original communication is hidden. Not only did he help in creating methods for encrypting information, but also decrypting information. And there were a lot of contributions that he made in that sense that a lot of people are attributing his work to the outcome of the world wars. And if it weren't for him and his contributions to cryptography, then the outcomes would have been significantly different. It says here he was convicted in 1952. Essentially, he was convicted for homosexual acts. Someone broke into his apartment and saw that he was living with another man. And back in England at the time, that was considered illegal. And so he was given, he was found guilty, and he was given a choice of either imprisonment or chemical castration. He opted for chemical castration, and a couple of years later, he committed suicide. He was a fan of fairy tales, and so specifically of Snow White, and so he ate a cyanide poisoned apple and committed suicide that way. A lot of people believe that that was wrong, and that considering all that he had contributed, not only to computing but also society in general, that he should receive a pardon. And so in 2013, Queen Elizabeth II gave him a posthumous pardon, and that came just about a year after people celebrated what would have been his 100th birthday. And as a student in the previous section highlighted, there was actually a movie that was developed about Alan Turing that was released, I think, in 2014, so it was approximately the same time, documenting his life and, again, his contributions to computing. Something that Professor Hofbauer wanted to include is a slide on Beatrice Worsley. And we've talked about the contributions of many other men and women, but one of the reasons why he wanted to highlight Beatrice Worsley is because she's important in terms of the contributions in Canadian computing history. So she is the first female computer scientist in Canada, and she got her PhD from the University of Cambridge. Alan Turing, whom we were just speaking of, was one of her advisors. This was before York University was started, and she joined the fledgling Department of Computing at U of T, and the first computer at a Canadian institution was educational institution, university, was at U of T downtown. And so that was brought over, and she wrote the first compiler for that machine. That machine was a Ferranti Mark I, and as we mentioned before, with respect to Grace Hopper, bless you, she invented the concept of the compiler, basically the ability to have your code be translated into machine-specific code so it could run your program on a variety of machines. Beatrice Worsley co-wrote the first compiler for the Ferranti Mark I, so that was able to take programs written for other machines and compile it on the Mark I and run it here. And so here we see that there's been a lot of contributions in the past by men and especially women in the field of computers. A lot of people wonder, well, why do we need to learn this? Why do we need to worry about this or concern ourselves about this? And I'm of the opinion that in order to really appreciate what we have today in terms of technology, the technology that we sometimes maybe take for granted, it's important to know where these contributions have been made, who's made these contributions, and how far we've come in relatively so little time.